Hi folks, welcome to the content review, day 2. Today we're going to be going through Chapter 5, Part A. Chapter 5, Part A was a longer portion of Chapter 5, so I wanted to make sure I spend adequate time on that. I'll go over Chapter 5B as well as what we did in Chapter 6 tomorrow. Alright, so Chapter 5, the first part of it, right, that started out with nth roots. And nth roots, if you don't remember, were they were like square roots, but you can choose any number instead of just 2. Well, any integer, any whole number, right? So, if we had something like, well, n equals 3 and a equals 64, how we'd write that is we write the root, all right, but it's an nth root. So we write a cubed root, because n is 3, right, of 64. And then, depending on who you had as your teacher, there were lots of different ways to simplify this. I think for me, the easiest way is knowing that 4 cubed is 64, so that the cubed root of 64 is 4. All right? So those were nth roots. Really, you just plug in your n and your a wherever they go and evaluate that root. After nth roots, we had rational exponents. And remember, rational exponents were where we wrote our exponents as fractions. And we wrote them as fractions depending on what their root versus their power was. So the power I always call m, all right? And the power of a function's always on the top of the fraction in terms of the exponent. All right, so this power is always going to be at the top of the exponent. The root is always in the bottom. It's always in the denominator. And how I remember that is that if we have flowers with roots, roots are always in the dirt with the denominator, but they get all of their power from the flowery part. So the power is up top, and in the dirt, in the denominator, is the root. Okay? So an example of that would be something like the cubed root of x, right, to the 4th power. So if we were rewriting this, we'd rewrite it as x to the power over the root. So my power is 4, my root is 3, so I'd rewrite that as x to the 4/3. And this rewriting aspect, both ways, was one of the biggest components of this portion of Chapter 5. All right, probably one of the most difficult concepts is the properties of exponents and radicals. All right, these are just a little tough just because there's so many of them, and unless you use them and practice them, if you don't practice with them, you're never going to get good with them. And I'll let you know, anyone that plans on going into anything in the STEM field is going to need to know how to do lots of manipulation with their exponents and with their radicals, okay? All right, so these properties had lots of different names, but the biggest takeaways here are some examples with them. All right? So, starting out, if we have something like 2 things that are being multiplied with the same base but have different exponents, like x cubed times x squared, then you always add the exponent. So you add x to the 3 plus 2, which is x to the 5. Now, this often gets mistaken for our next rule, right? So this is called product of powers because there's a product and there's powers. This is called power of a power because there's no product and it's just the power of a power, all right? Now, power of a power says instead of adding your exponents, you're going to multiply them. So that gives us x to the 3 plus 2, or x to the 6. After that, we came to our next one, which I always think of as kind of like the distributive property. So if you have 2 things that are being multiplied inside a parenthesis set, and there's an exponent on the outside, what you're going to do is distribute in that exponent to each piece. All right, so my 5 gets a squared, and my x gets a squared. That was probably one of the biggest mistakes I saw, is like a lot of my students at least were like, yeah, I'm just going to apply it to the x squared. Who cares about the 5? But the 5's important too, all right? So if you square the 5, you're left with 25. X squared is your final answer. All right. Then we came to some stuff with some negative exponents. And remember, anytime we have like x to the negative m or something, right? That's the same thing as 1 over x to the m. So all you have to do is bring your term into the denominator, but it's only the term that has a negative exponent. So I have this negative 2 as my exponent, and that negative 2 is only on the x, all right? There's no negative 2 up here with that 3, and there's no parentheses around it like our previous example. So that means the only thing that has that negative 2 as an exponent is the x. So that means the 3 still stays up top, but on the bottom, we're left with x to the positive 2. So you see, just like in this example here, we had x to the negative m, and we rewrote that as x to the m, right? Or 1 over x to the m, I should say. Like when we move the exponent down into the denominator, then it changes the sign. Or vice versa, if you had like a negative 2 down here, you could move it up into the numerator and change the sign. All right? Okay, then we came, so that was our negative powers rule, and then we came to the 0th power. This is probably one of the most powerful because anything raised to the 0th power is just 1. All right, so that means you could have 253 raised to the 0th power, and it's still just 1. Even if it's like 253 times x to the 5th, all raised to the 0th power, still just 1. All right, so that one's pretty powerful. All right, so we dealt with some multiplication in our earlier properties, but then we have to get into some division as we moved on. So the biggest piece of division was something like this, right? An x to the 5th over an x cubed. And I know some of you still struggle with this because some of you are struggling with it in chapter 6. All right. Remember, anytime you have an x, like an x to a power over an x to a power, you can always cancel them out, right? The old way that we would do it is that we had x times x times x times x times x. So we have 5 x's on top and 3 x's on bottom. And then we'd cancel one of the x's on the bottom with one of the x's on top, so on and so forth. So we could do it that way, but that gets a little tedious when you get to like x to the 43rd power, right? So instead, the easier way to do it is just like earlier, right? When we had things that were multiplied together, we added the exponents. When we have things that are divided together, we subtract the exponents. So we're left with x to the 5 minus 3, or x squared. And that's the same answer you'd get by canceling out. All right? Just like we can distribute into just like we can distribute into a multiplication, we can also distribute into division. All right, so I'm going to take this squared and I'm going to distribute into this x, but I'm also going to distribute into that 3. All right, like imagine that, like you're out, like if this is confusing for you, if you, that's a very bad stick drawing. But if you were with a friend, right? And your mom made you guys 2 cookies each, right? But you only got 2 cookies and your friend didn't get any cookies, right? Like then you're left with like those 2 extra cookies. And I know that that's like a silly example, but like for me it helps to remember that like the x and the 3 are together, and so we should treat them the same. All right? So then we're left with an x squared over 3 squared. But we don't leave 3 squared as 3 squared because we know it simplifies down to 9. So we're left with x squared over 9 as our final answer. All right, our last 2 properties had to deal with radicals. And I left them in terms of the nth root of a times b and the nth root of a divided by b because I wanted to make sure you remembered that these could be any roots. You're going to see them most often with square roots, and in algebra and pre-algebra, you did simplification with some of that, right? But these can apply to any roots. They can be the 5th root, they can be the 56th root, right? So, if we had something like the 4th root of, I don't know, 5x cubed, right? This is a bad example because neither of those simplify. But we could split that up into the 4th root of 5 times the 4th root of x cubed. And while this doesn't seem to change things too much, you could, if you were working on this in a problem, then change this into a radical or a rational exponent, which would be helpful depending on what the rest of your problem is. All right, so this is a really great simplification tool. But just like you can break up multiplication, you can also break up division. All right, so if we had the 4th root of, let's say, like 81 over 81 over 16, all right? We could split that up into the 4th root of 81 over the 4th root of 16, right? And the nice thing is then we can simplify all of those individually, which is a super important thing, right? So the 4th root of 81/16 it doesn't simplify. But the 4th root of 81 is 3, and the 4th root of 16 is 2. All right, so like that's what I was talking about with my my multiplication examples. Like that's not a super great one in terms of like it doesn't simplify down nicely, and also you can still see the value of it. All right, so those were all of your properties of rational exponents and of radicals. And we used those a lot, especially in the second half of chapter 5. But what we ended with in the first half of chapter 5, right, is this transformation of radical graphs. And we learned how to transform graphs when we were working with like an x squared or an absolute value of x back in the first trimester, right? Or like trimester A, I should say. And we learned that like a quadratic or an absolute value can be treated as a parent function which can be manipulated. Well, square root functions or radical functions can do the exact same. So you see that in blue I have written y equals the square root of x. That's our base function, right? Our most basic parent function. But then we had lots of things to go with it, right? So our most general form of our y equals square root of x equation is y equals negative a times the square root of x minus h plus k. Remember, this negative sign is a reflection, all right? If a was bigger than 1, we called it a stretch. And if a was less than 1, we called it a shrink, right? If we had x minus h, we were going to the right. And if we had an x plus h, we moved to the left. And then plus k took us up, and then a minus k took us down. Right, so the cool part about transforming radical graphs is that it makes them so much easier to graph, right? If you just learn how to transform them, it's a lot easier to work with them. So we know that, if we reflect it, it's, reflected across the x-axis, right? If we had a stretch, which makes it steeper, it looks something like this. Whereas if we had a shrink, which makes it shallower, it would look more like that, all right? And then the h and the k, remember that h moves it horizontally left and right, and k moved it vertically up and down, all right? Now the big takeaways from here are your domain and range, all right? So you see in our graph, I'm going to go ahead and take off our extras that we just drew in. Okay, so you can see in our basic form of our graph, for our domain, the restrictions on our domain, well, are that we have a square root function. And since we have a square root function, we know that we can never have negative numbers. And that makes sense when you look at the fact that the entire negative half of the graph is completely blank, all right? So our domain will be that x is greater than or equal to 0, all right? And we say greater than or equal to 0 because that's telling us all of the numbers that we're plugging in are bigger than or equal to 0. All right? Now, if this were instead the domain of like an x minus h, right? Then you set x minus h greater than or equal to 0. All right, which means that x is greater than or equal to h. Okay? And that makes sense because if you plug in h for x, you get h minus h, which is 0. So it's still bigger than or equal to 0. It's just looking at the numbers we're plugging in. Now your range depends on if you have a negative. So if you have a negative, all of your y's will be less. So if this is a negative a, or if you had positives, your y would be greater than. All right? And it's always related to that k value. All right? So y is either less than or equal to k if you have a negative sign, or a negative sign in front of the a, or that y is greater than or equal to k if you just have a positive, if there's no reflection. So that's all we had for our work in Chapter 5, Part A. All right, so stick around for tomorrow for Chapter 5, Part B.